All right, let's get started. Good morning, everyone. Today is April 21st. 420 was yesterday. So, uh, we are solving the homework for chapter 6, mobile equipment, power requirements, today. And we will solve the problems of the last chapter that we covered, which should be chapter 10. Actually, it's a few chapters, 8, 9, and 10. On Friday and the coming Monday, we will have the exam, okay, exam 2. So without further ado, let's make the most out of the time. Let me go ahead and share the screen and we can get started. Lots of PowerPoints open, but this is the one I need. Okay. So, all right. So, before we get started, let's have a quick review of some of the main concepts we need to solve these problems. The first one was the concept of resistance. We said that there are two different types of resistance when the machine is moving, when the equipment is moving. One is the rolling resistance, which exists between the tire and the surface of the road. And that depends on the road surface condition, the tires, the penetration of the tires, and stuff like that. Okay. Grade resistance, as implied by the name, is all about the grade, the slope. Okay. Is given in percentages. When it is 3%, it means for every 100 feet, you are going up for 3 feet if it's positive. And if it's negative 3 feet, 3%, it means for every 100 feet, you're going down for 3 feet. So therefore, the required power must be greater than the resistances, okay, the resisting forces. The total resistance is the summation of the rolling and the grade resistance, okay? And for the machine to move, it has to overcome the total resistance, which is again the RR or rolling resistance plus GR or grade resistance. That's the main concept. Okay. In other words, from the power that the machine generates, okay, a good portion of it is to overcome the resistance. The remainder is actually be the usable power. Okay. So the usable power is the entire power that the machine generates minus the power that is used to overcome the resisting forces. These are the main concepts. These are the fundamentals of chapter 6. So we also said that if we have the grade in percent, and if it is less than 10%, we can easily find the grade resistance, okay? Which is usually the case because we are rarely talking about grades higher than 10% in construction because we're working with very super heavy equipment. So we don't want high slopes. That's why we keep it less than 10%. And if that's the case, you can easily find the grade resistance. All that you need to know is the weight of the vehicle. So once you have the weight of the vehicle, you use this equation, okay? For example, if a machine weighs 50 US tons, you put 20, so this is for every US ton, 20 multiplied by the grade in percent, but this guy is 50 tons, so that would be 20 multiplied by 50 multiplied by the grade, which is 7% in this example, okay? So for 1 ton, for every ton of the vehicle, the grade resistance will be 20 times the slope in percent. And since this is 70, this is 50 here, so you put 50 here as the weight. This is 50 times more than this guy. This is for 1 ton. Okay, so that's the idea. That's how we find the grade resistance if the grade is less than 10% which is often the case. Okay. We also said that we could find the equivalent rolling resistance. Rolling resistance is usually given in pound per ton. It means, sorry, in, what was it? Yeah, pound per ton. It means the force per every ton of the vehicle, okay? But we could also convert rolling resistance into an equivalent grade resistance, okay? For example, we add actually, for example, if the rolling resistance, if the grade resistance is 3% and the equivalent rolling resistance is equal to a slope of 2%, we could consider we are having a slope of 5%, okay? So it means we convert rolling resistance into equivalent grade resistance to be able to sum them up as one number that shows the combination impact, the combined impact of grade and rolling resistance in percent of slope. That's the main idea, okay? So the total resistance is this. Don't forget the negative sign. It could be, so the grade could be a negative number if you're going down. It means your resistance is getting deducted, okay? You will have less resistance when you're going down, or you will have more usable power when you're going down, okay? So we can convert the rolling resistance to an equivalent gradient. In order to do that, all you need to do is that you divide the rolling resistance, which is given in pound per ton, US ton, of course, you divide it by number 20, okay? And this will convert rolling resistance into the equivalent grade resistance. Does that make sense? Okay, and once you have the equivalent rolling resistance, you can add it with the grade resistance and it will give you the total resistance. I'm using the word resistance so many times. Okay, so let's get started because I'm not, that was a quick review of the main concepts of chapter 6. Having those few equations and knowing that concept, you should be able to solve all these problems. Let's take a look at the first one. You're talking about these Ferrari, super nice vehicles. The price in that time was almost 46,000 euros. It's a V12 engine, okay? And it's rated at 808 horsepower. So this horsepower is needed because when we are finding the rim pull, okay? Your new car has a maximum speed. This is also needed when we are considering the rim pull, and this is RPM. This is also required for rim pull. So having these three, we could have the rim pull. Determine its maximum rim pull, then operated at a maximum speed of its engine efficiency uh, of 90%. Okay, so the machine, when it is at its maximum speed, is using 90% of the engine capacity. So the Ferrari weighs, this is the weight of the machine, okay, and is operated over a concrete road with a rolling resistance of this much and the slope of this much. So the rolling resistance is given, but not in the gradient, okay, the equivalent gradient, but in pound per US ton, and the slope is also given. Determine the maximum external pull. So we first need to find the rim pull, okay, the power that the machine generates. But from the power that the machine generates, a good portion of it will go to overcome the two resisting forces of rolling and grade resistance. So we need to find those two powers and deduct it from the power that the machine generates, and that will be the usable power of the machine. Okay, so let's get started with that. Determine the maximum rim pull. We have one equation for the rim pull that has the horsepower, that has the RPM, and that has the engine efficiency at maximum speed. So we also need the speed. So this is the equation we use to find the ripple. 375 is the constant, horsepower should be put here. Efficiency, which is in this case 90%, is on top, and the speed must be in mile per hour. So we need to make sure it is in mile per hour. No, it is in kilometers per hour. So we have to first convert kilometer per hour to mile per hour. 340 kilometer per hour must be divided by 1.6 kilometer. There is 1.6 kilometer in every mile. So the machine could move 211 miles, wow, per hour. This is really high. So yeah, all right. So the ripple now could be easily found because we have the speed in mile per hour. So all we need to do is to insert the numbers we have into the equation. 375 was the constant, the horsepower was given as 808, the engine efficiency at maximum speed was given as 90%, so not the entire power is, not the entire capacity is used, but 90% of it. And the speed is in mile per hour, so we could simply put it here. The number we find is this number, 1,291 pound is the ripple the machine is generating in this speed, okay? In the next step, we should find the resisting forces, okay? The resisting forces are two. One was the rolling resistance, which is given in pound per ton, and the other one is grade resistance. Okay, so the strategy is to find the total resistance, which is the grade plus rolling resistance. We first find the force needed to overcome the total resistance. Okay, and then deduct what we find here from the ripple that the machine generates. Okay, so we deduct what portion or how many pounds of the machine force is being used to overcome the resisting forces, and the remainder will be the available pull. Okay, again, not all of the force that the machine generates is usable or is available. A big portion of it will go to overcoming resisting forces, and the remainder of it is called the available pull. Okay, so we need to find the total resistance first. Total is grade plus rolling resistance. Starting with grade resistance, we need to find the weight of the car. Okay, the weight of the car in US tons. Okay, so we simply divide it by 2,000 because there are 2,000 pounds in every ton. So this is the weight of the vehicle. It's 2.08 tons, and we have the grade. Remember the equation we said, if we have the weight of the vehicle and if the grade is less than 10%, which is often the case, we could easily find the grade resisting force, or the grade resistance. The grade resistance will be the weight of the vehicle uh, multiplied by the grade multiplied by number 20. Okay, so we could have the grade resistance there and the rolling resistance. Okay, for to find the rolling resistance, um, we have we have this equation. Okay, so here, since the grade is given as 3%, we just keep it because we want to have the grade in percentages. And actually we will convert the rolling resistance into the equivalent gradient, so we could easily add them up. Okay. Okay, so let's see. The rolling resistance is what? We have this rule that if the rolling resistance is given based on pound per ton, you could easily convert it into the equivalent gradient. Okay, and this here, we have this story. So 40 is the rolling resistance, 40 pound per ton. So we could easily divide it by 20 pound per ton, and the equivalent rolling resistance will be 2%. Now, both of them are in percentages, so we could easily add them up. The total resistance will be 3 plus 2% or 5%. 5% is still less than 10%, okay? So we could use this rule that 20 multiplied by 5 multiplied by the weight of the machine here and then here. But instead of that, to make it easier, we first find the resulting grade, okay, which is the summation of the two grades. One was given, one we converted. This is the resulting grade. And since it is still less than 10%, we could use this rule that for slopes of less than 10%, we can easily find the force required to move the car by using this equation, okay? 20 multiplied by the weight of the vehicle in US tons multiplied by the percent of the grade percent, actually the grade, okay? So 208 or 208 pound is the force required to move the car. Now, the maximum available external pull in the sixth gear is what? It is the power that the machine generates, and that's the rim pull. We found it in the previous step. It was 1,291 pound, of which this much it goes to overcoming the resisting forces. Okay, the summation of rolling plus grade resistance. So this is the power the machine is generating. This is the power that is required to overcome the resistance. The remainder is the usable power of the car. Okay, so this will be the usable power of the car. Any questions? All right, so let's move on to question two. Question two says we have this CAD 834H four-wheel tractor, and it is moving with rubber tires and high pressure. This is given because um, it wants us to use a table. Okay, that's why it is giving us this information. With an operating weight, so the weight is given in pounds, we probably need to convert it into US tons somewhere, is pulled up a road whose slope is 3%. So we have the slope, we could easily have the grade resistance because we also have the weight of the vehicle. If the average tension in the towing cable, so here the machine is not generating any force. We're not talking about rim pull. We are talking about towing this machine. So we are towing this machine, and there is the pressure in the towing cable is shown as 660 pounds. Okay, so this will be the combination of the rolling resistance plus the grade resistance. Now it is asking us what is the rolling resistance. So this is the total, and we could find the grade resistance, and the remainder will be the rolling resistance. Okay, so sounds like an easy problem. We have the total resistance, we have the information needed to find the grade resistance. So total minus grade will give us the rolling resistance. So yeah, when you're doing these problems, please watch them in full screen so you can easily follow the steps. I actually have tried to make these solutions as easy to follow as possible. Okay. All right. The machine is pulled, so the tension in the cable will show the summation of grade and rolling resistance. Since we have the slope, we can easily find the grade resistance. Slope percentage multiplied by the weight of the equipment will give us the grade resistance. So it's 3%. This was the weight. We can use it in pounds. We need to use it in pounds. So this will be the grade resistance in pounds. Okay. So far so good. We have the grade resistance and we have the total. So tension in the cable, again, what is the total resistance? So which this much goes to grade resistance. Of the total, this portion is for grade resistance. Therefore, the remainder is for rolling resistance, okay? So we say that 660 pound, which is the total, minus 3,245 pounds, which is the grade resistance, gives us 2,815 pounds, which is the rolling resistance. Okay, so now we do have the rolling resistance and we are done with part A. But part B is asking tricky questions. It's asking, this would be what type of road surface? Okay, so we have the rolling resistance. We know how much it is. We also, uh, yeah, we have the rolling resistance. We also know what kind of tires we are using. Okay, so we need to use one table, and that table will be the table that correlates the rolling resistance to the type of tires, okay, type of machine tires. But that table uses the numbers based on tons, not pounds. So the first thing we need to do is to convert this force, which is given in pounds, to tons, okay? So um, we simply divide that force into, we simply first find the weight of the tractor in tons. So the weight of the tractor was in pounds. We need to divide it by 2,000. So this is the weight of the vehicle, the weight of the, equipment, which is 54 US tons, okay? Now we can find the rolling resistance based on tons, okay, based on pound per ton. So this is pound, this is pound, this is the rolling resistance in pound, and this is for the entire machine, the entire weight of the machine. But we want to know the rolling resistance per 1 ton, per every ton of the machine. So since this machine is 54 tons, okay, we need to divide the entire rolling resistance given in pound to the weight of the vehicle, the weight of the equipment, and it gives us the rolling resistance based on pound per ton. Why should we do this? Because we're using this table, and this table gives us the rolling resistance based on pound per ton, okay? Or kilogram per meter, kilogram meter in every ton, okay? So we don't care about this one. We want the pound per ton. We had the pound and we divided by the weight of the vehicle in tons, and the number we find is 52. Now, where to find our number? We need to look at the type of the tires we have. So we have rubber tires with high pressure. So we're not talking about steel, we're not talking about Crowler, we're talking about rubber tires. And between low and high, we need to use rubber tires and high pressure. And between these two, not this guy, but pound per ton is what we're looking at. The number we have found, so we do have the number. We want the type of the surface. That is what is wanted, okay? So having the pound per ton, uh, our number is 52. We should see where it falls. It could fall into this range. Number 52 falls into this range, but it could also fall into this range, okay? So we could say the type of the surface is either good asphalt or it is earth compacted and maintained. So the surface condition is almost good, okay? Because we are having, uh, this is not a significant rolling resistance. This is a low rolling resistance, which shows that the surface condition is good. As you can see, for smooth concrete, we have the lowest rolling resistance, and that makes sense. And for very muddy and uh, rotted or soft soil, why soft soil is bad? Because the tires can penetrate into the soil. If you remember, I said, imagine riding your bicycle on the seaside, okay, on sand. So your tire penetrates into the soil and it becomes a lot harder to pedal, to move it, okay? So that's why soft soil has a higher rolling resistance. But this is good asphalt and the rolling resistance is relatively low. Any questions on this one? All right, so yeah, based on this, we are talking about the surface must be either good asphalt or compacted and maintained earth. Let me find this question. So the answer for part A would be 52 pound per ton. For part A was asking the rolling resistance, and we found it as 52 pound per ton, or actually, the part A is done here. Okay, this is the rolling resistance. The reason we converted rolling resistance into pound per ton was that so that we will be able to use this table, because in this table rolling resistance is given based on pound per ton, so we had to make one conversion to use this table. Does that make sense, Thomas? Okay, so let's move on to the next problem. So we have another CAT machine, 834H four-wheel tractor. This is the weight of it in pounds, and it is equipped with a converter drive. Uh, is equipped with a converter drive of 523 horsepower. So we probably will need to find the Rimple, because whenever horsepower comes into play, we probably need to find a Rimple, or not. Maybe it's just extra information. The table below shows the maximum speeds for this machine in each of its four gears. Well, I didn't put the table here. It should be in the next slide. Determine the maximum Rimple. Yes, the maximum Rimple of the tractor in each of the indicated gears. Well, for that, we also need the efficiency. Um, yeah, the efficiency of the engine. It is also given as 92%. Okay, so we could do that. And then the next part, it says if the tractor is operated over a haul road with this slope, positive 2.5%, with rolling resistance. So rolling resistance is ready to use. It's 80 pound per ton. Determine the maximum external pull. So this is um, actually the usable pull, the usable power of the machine. So in part A, we can find the pull that is generated. In part B, we should find the summation of the resisting forces and deduct it from the generated pull. The remainder will be the usable pull. And part C is asking, can the tractor climb the slope in the fourth gear? Well, the pull should be a positive number. If it is a positive number, it means it can go up. If it's a negative number, it means it cannot generate enough power to overcome the resisting forces. All right. So part A was asking to find the maximum Rimple. So we know the equation needed for Rimple. Uh, that is the power, okay, and the efficiency of the engine, okay. And we also know I was worried about the horsepower, because the problem. Let me see. Yeah. Oh yeah, it's given actually. Yeah, the problem. gave the horsepower as 523. Sorry, my PowerPoint is being slow. All right. Yeah. 523 was the horsepower and it was given. And 375 is the constant. 92% is the efficiency also given. And the corresponding speed in each gear is given in a table. Okay. So this is the table that tells us the speed in each gear. Okay. So in the first gear, it can only move at 4 miles per 4.2 miles per hour. So all we need to do to find the ripple, because it is asking the ripple in different gears, okay? And the only thing that changes in different gears is the speed of the vehicle. So we'll write the equation, everything will be remain the same except the speed. So the speed changes, as the speed changes, the ripple changes. So we expect that as the speed increases, the ripple decreases, right? Because the speed is in the denominator of this fraction. So let's see if that is the case. Yeah, I have done the computations. So in the first gear, the machine is generating the maximum ripple of 42, almost 43,000 pounds. But as you can see, in second, third, and fourth gear, the ripple continues to decrease. So it is the trade-off between the speed and the power. The faster you want to go, the less speed, the less power you will have. Okay. If the tractor is operated over a haul road and its grade is given as 2.5% with rolling resistance of 80 pounds per ton, determine the maximum external pull. Again, the thing we need to do is to find the total resisting forces and deduct it from the power that the machine generates. Okay, so weight of the tractor should be first converted to tons. That's why you just divide the weight given in pounds by 2,000, and the result is 54 tons. Super heavy vehicle. I'm sorry, equipment. So the slope is 2.5. It's less than 10%, and the rolling resistance is given as 80 pounds per ton. So how about we convert the rolling resistance into the equivalent gradient first, then add it with this, and then convert it to, then find it in pounds, okay? So yeah, we first uh, find the rolling resistance. We need to convert it into the slope. So that would be equivalent to 4% slope. Now, 4 is the rolling resistance, which is converted into the gradient. And 2.5 was the grade resistance. So the total resistance is 6.5%. So 6.5% of the ripple, 6.5% of the weight of the vehicle, okay, would be this much, okay, would be this much. Let me see the question. Where did the come from? That was the weight of the vehicle, and that was given. Let me show it to you. Oops. The weight of the vehicle is here, okay? Second line. So that's where we find the weight of the vehicle. So, I keep saying vehicle, it's equipment. So yeah, so the total resistance is 6.5. 6.5 multiplied by the weight of the vehicle is this much. Okay, this is the actually the ripple required to move the tractor. In other words, this is the total resisting forces. Okay, so we already had computed the ripple in the previous part. Remember, we had this column 2. But this is the power that the machine generates. If I go back, so we're just considering, we're just using this equation, okay? We are not considering any resisting forces. So regardless of the forces, of the resisting forces, this power is being generated by the machine. But we now know that a good part of it, or 7,000 pounds of it, should be consumed to overcome the resisting forces. So in each line, we have to deduct this number from the rim pull that the machine generates, and the number we find will be the maximum available pull, okay? So the power that the machine generates minus the power needed to overcome total resistance is the available pull, okay? And as you can see, uh, in the first gear, we have the maximum available pull, and it goes down and down, okay? Let me take this question. Then we only need to do this for the first gear. Let's see, determine the maximum pull by the tractor. Yes, you're right. The problem is asking us to find the pull for the first gear, but I just wanted you guys to know, or what I wanted to show you, that the available pull also decreases as we move faster. All right, let's move on to part C. Part C is asking if the tractor can climb the slope in the fourth gear. Okay, so this is our table. This is our table. And in the fourth gear, we still have a positive number. It means, yes, we can still move up the slope. And this was an animation. The Snoop Dogg was doing like this. It means, yes, we can. So the answer is positive. Now, that problem is done. Do you have any questions? Any issues with that? Okay. Next problem is saying a fully loaded cat scraper is operating in its fifth gear, okay, at its full rated RPM, ambient air temperature 60 degrees of Fahrenheit. We probably won't use it in this problem. The scraper is climbing a uniform 4% slope with a rolling resistance of 70 pounds per ton. And the pneumatic tired scraper bowl is fully loaded with the material. So this information is provided by the manufacturer, okay? And using that, we want to find the weight of the vehicle, the weight of the equipment. What is the total operating weight of the fully loaded scraper? So that could be, that could be found by considering the weight of the equipment when it is empty plus the weight of the payload, okay? So that would be the summation of the total operating when it's empty. It means we are excluding the payload weight, and then we add it because we have the number, okay? So other numbers like total operating loaded and these numbers, because it's not, we didn't talk about total operating. So other numbers will not be the right choice. The best choice is that if we consider the empty weight and then we add the payload. So the summation of both will be 126,000, almost 126,000 pounds. Now, why do we need it? Because we will probably be working with, the pull the machine can generate. What portion in pounds and percent of the fully loaded weight is carried by the front axle? Well, that's an easy question because all we need to do is to see how much of the total operating load is yeah, is carried by the front axle. Okay, so that would be 67 whatever divided by 126,000. So we need the percentage. So 50, almost half of the equipment's weight is on its front load, slightly more than half. Okay, front axle. So what portion in pounds and percent of the fully loaded weight is carried by the rear axle? That could also be found easily. So that would be 126. It was the total. And the rear axle is this. Okay, so we divide 59,000 by the total operating load of the machine. That gives us 47%. Or we could simply say, so we only have two axles here, 53% is actually carried by the front axle. So the remainder will be carried by the rear axle. So 100% minus 53% would be 47%. Or we could just do the math either way. All right. What is the total resistance? For total resistance, we first convert the weight of the vehicle from pound to ton by dividing it by 2,000. It will be 63 tons. Rolling resistance is 70 pounds per ton. For 1 ton, it is 70 pounds. So this equipment is 63 tons. That's why its rolling resistance is this much, 4,431 pounds. Grade resistance could be also found by doing the percentage multiplied by 20 multiplied by the weight of the equipment in tons, and it will give us the result in pounds. As you can see, the grade resistance here is more than the rolling resistance. That's most of the time the case if the grade is more than 2 or 3%. Okay, so unless the road's surface condition is poor. So the total resistance, now both of them are in pounds, so we could easily add them up. The resulting number is almost 9,500 pounds. Okay, or what you could do, the other thing you could do is that you could do the equivalent grade. So for that, you would do 70 divided by 20, okay, to convert the rolling resistance into the equivalent gradient. And then the rolling resistance was 4%. So the summation of them would be 7.5%. And it is still less than 10%. So we can use this rule, okay? So we simply multiply 7.5 by the weight of the vehicle, the weight of the equipment in tons, and the number 20, which is the constant in this equation, okay? It gives us the same exact number, as you can see, okay? So either way, we could find this number. Next problem is, actually it's the rest, yes, it's part E of problem 4. What is the value of the coefficient of traction? So remember coefficient of traction, we had an equation for that. Let's first convert the weight on the drive wheels or the front axle. So we know 53%. Okay, so this was actually the tricky part. What's the value of coefficient of traction? If the drive wheels of the vehicle, of the tractor, are at the point of slippage, okay? So drive wheels are on the front axle, okay? So you should not consider the entire weight of the equipment. You should consider the part of the weight or the portion of the weight that is carried by the front axle. So we know 53% of the entire equipment weight is carried by the front axles. that is equal to 67,000 pounds. This is the portion, this is the weight on the front wheels or front axle of the equipment. Now, we know the usable force is the coefficient of traction multiplied by weight on powered running gear. Okay, so this is why we did this, because we need to, when we are using this equation, you should not consider the entire weight of the machine, of the equipment. You should consider the portion of the weight that is on the running gear, okay, on the weight on the powered running gear, okay? So the tractive effort, therefore, is because we had the usable force and we had the um, yeah, the tractive effort required from the previous part. Um, we actually had these two numbers in the previous parts, so it will be 0.14. Okay. So the only part that was a little tricky was this 53%, because you should consider the portion of the weight that is carried by the running gear according to the equation. And the problem, maybe the problem did not ask us upfront that what portion of the weight is being carried by the front axle, but you still had to do this, okay? Because in the last part for using that equation, you should put the portion of the weight that is carried by the running gear. All right, so next problem is about using the chart. The first part of the problem is pretty much similar to what we did. The total resistance is grade plus rolling resistance. And in this problem, it was a flat surface, I guess. Let me check. Yeah, a wheel tractor is operating on a level grade. When it says level grade, it means the grade resistance is 0. So the entire resisting force will be the rolling resistance. So total resistance for 15 miles per hour. Let's find it. The first thing you need to do, let me put this aside, for 15 miles per hour. This is 15 miles per hour, okay? So you first draw this line, then since it is moving in, let me see, what is it moving? What is speed? Speed of 15 and the maximum value of coefficient of traction, okay? All right, okay. So let's go back to the problem. Yeah, so this is the line. This is the load, actually. This is the load. So, and this is the line. They intersect here. And as you can see, the number, so this is the intersecting point between these two lines. And this will give us the rolling resistance from the table, okay? It falls somewhere between 5%, but closer to 6%, okay? I read it as 5.2, and this is an estimate. So 5.2 is the rolling resistance, and according to the to that rule, that if it is less than 10%, you could use this equation. So we can find the rolling resistance as, I mean, we could convert the rolling resistance from percentages into tons, okay? Pound per ton. Yes. So let me see how much time. Okay, it's 8:59. I pretty much finished this. I guess there's only, yeah, there's only one more slide. Let me finish the last slide. The last slide is that, okay, from figure, we found that the total resistance, um, no, it will be in a rush. So let me do this in the next time, okay? So the last slide of, or the part B of question 5, I will do on Friday, plus I will solve the the last homework number 7, and the exam will be on Monday. Um, I will not post these slides for the homework, but I will post a video, okay? So you can have access to that. Alrighty, so that completes the class today because I want you to see my explanations, and I will most probably put it on YouTube because for some reason Canvas is not allowing me to post more items because we have posted too many items, so my capacity is full. All right, all, have a nice one, and if you have questions, I will be in my office today. Just feel free to stop by.